Looking to the mass spectrum, the most prominent peak is at 45. Based on that information and looking to other visibly prominent peaks from the range of 36 to 60, we were able to then determine various fragments which compose the molecule in question. Though there are peaks signaling masses in the range from 70 to 362, we determined that they are insignificant in comparison to the more visibly predominant peaks, concluding that these peaks resulting were from traces left over in the mass spectrometer from the previous test, therefore not a component to our unknown molecule.
With a predominant peak at 45, we knew that one of the main fragments of the entire molecule must have a mass of 45, which corresponds to a C2H5O atom. Using the C2H5O fragment, that was the essential part of the molecule, we determined that the molecular peak at 60 had an additional CH3 group, which added a mass of 15. Therefore, the molecular formula of the molecule derived from the mass spectrum data was C3H8O. Additionally, a mass spectrum of isopropyl alcohol, or C3H8O, accessed from a database from the National Institute of Standards and Technology, has a nearly identical mass spectrum to the mass spectrum we were given, supporting the idea that the molecular formula of our given molecule is C3H8.
In the NMR spectrum, since the integration numbers of peaks A, B, and C total at 8, we determined that 8 hydrogens were in the molecule. With both signals A and B, the integration number is 1. Therefore, we concluded that the hydrogens were either a part of a CH or OH bond, whereas a signal C with the integration number of 6 would likely be signaling 2 CH3 bonds.
Good. The shift table from California State Polytechnic University shows the variability of an OH bond's potential shift. Since peak B has no neighboring hydrogens due to having only a singlet, it corresponds to the OH bond. Peak B has a chemical shift of approximately 1.5 ppm, which exists within the potential range of an OH bond's shift, which is from 0.5 to 5.
The chemical shift of A at 4.0 ppm is indicative of the hydrogen being in close proximity to electronegative atoms such as oxygen, while the shift of signal C at 1.2 ppm is less proximal to the oxygen atoms. The splitting then indicates that signal A with 7 peaks has 6 neighboring hydrogens, while the single peak of B has no neighbors. The doublet of C then has 1 neighboring hydrogen. This implies that the single hydrogen of A is likely neighboring the 6 hydrogens of C.
In the predicted NMR spectrum created on ChemDraw, it is seen that the peaks are nearly identical to the peaks in the NMR spectrum that was tested here at the U of A. The lowest peak is a doublet near 1.2 ppm, and there's a peak with 7 splits slightly above 4 ppm. The only difference between the two peaks is that the simulated ChemDraw NMR has shifted the peak corresponding to the OH bond to near 5 ppm. However, ChemDraw also shows that this is a rough estimation of where the signal would actually be located in the real data, and is due to the variability of OH shift.